Good morning, everyone. We are the positioning professionals, and our project is a 3D optical positioning system. This is Nathan, our hardware engineer, Russell, our software engineer, and Abdullah, our mathematician, and I'm Dhiren, the team lead, and Mikhail, the microcontroller engineer, and also the documentation manager, and he's going to tell you more about our project.
So when we were first given this topic, we looked into the market and we saw that a lot of localized positioning systems were part of a bigger cohesive system looking like a Wii or an Xbox Kinect, where the actual positioning was abstracted from the user and used by the system itself. So we saw this gap and we decided that we'd develop something that would act as a pure positioning subsystem, so that if a user wanted positioning data for a bigger project, like a flight controller, where you can use, say, a 3D mouse for tilting and raising, you can just use our subsystem to get the raw data, and using the position values it generates, you can proceed with whatever larger project you want. And so, as you can see in our middle, we have our prototype, which consists of a PCB with 4 IR emitters that are aimed at a base pad which contains 2 photodiode-based sensors. These sensors measure the angle of incident light and use that to calculate the position of the 4 LEDs, which is then displayed by a GUI. Looking at our system design diagram, first we have a UART broadcast to our system that says our device is connected. Once our device is connected, we send another UART broadcast to calibrate our sensors to calibrate out any ambient IR light that may be interfering. From there, our microcontroller takes over and selects one of the 4 LEDs. Then it tells the sensors to pull down the current driver within it so that they can sample that specific LED. This goes through for both sensors and for all 4 LEDs. And then we pull the data from the sensors using I2C to the microcontroller. The microcontroller pushes it to our Unity-based software using UART. And from there, we filter the data. We apply some characterization because the sensor response isn't necessarily linear. And we use the angles to calculate the position and display it on the GUI in approximately real time. So we have metrics of cost, power, range, accuracy, speed, and eye safety. We met all of them with the exceptions of range and speed. The range metric was fundamentally limited by the sensors themselves. The sensors are designed to be reflection-based gesture sensors with a range of only 15 centimeters. Our target was 30 centimeters. So far, we've achieved 22 centimeters, and we're trying to improve that continually by recharacterizing for different vertical heights, because as intensity drops off quadratically, the sensors are even worse at characterizing specific angular measurements. They're designed for differentials to get gestures. And as for our speed metric, the main limit there was the microcontroller's slow I2C. So we can simply swap out that microcontroller for an E-series, which supports 3.2 megahertz I2C, which will increase our sampling rate from about 38 hertz for an entire position sample to upwards of around 200 or 175 hertz. Any questions?
Yeah, usually in light systems, your ambient light just kills you. I mean, that's one of your biggest problems. What did you guys do about the ambient light?
So the sensors, their quantum efficiency is a very narrow band of IR, which is what our LEDs fall under. And in addition to that, the sensor has a calibration procedure where it takes the values that are output from the angle measurements, and you can tone those down repeatedly using offsets.
Did you pulse it and use some sort of a discriminator and a filter?
The sensor is relatively well integrated, so it has all of that circuitry built in within it.
Oh,
so
you bought a sensor like you'd use for like a TV remote or something?
We use the ADUX 1020, which it's not as much an IR receiver. It measures the angle of incident light on it, and it gives you that result. And you can use that result from multiple sensors and multiple LEDs to be able to get your position. And so that sensor, it has configuration for both incident angle X and incident angle Y, and that was adjusted before the system started running to account for any ambient IR light that may have interfered.
So your technique is you periodically recalibrate for whatever to compensate for whatever the ambient light is.
We found that we didn't need to periodically recalibrate,
Found
but
it hard to believe, but okay.
yeah, because when we left this running for perhaps an hour and then came back to use it, and so our calibration target is we'll just say 100, because if you're not using the sensor, that doesn't really mean anything. But our calibration target is 100, and normal operation creates intensities of around 4,000 to 8,000. And after we left it running for an hour and returned to it, the baseline intensity readings were still below 200. So unless you have direct IR interference, then it isn't a problem. And we also have 4 LEDs to add some sort of redundancy mechanism if you accidentally occlude one of them, since you only really need 3 to calculate a plane to get your position values.
Do you have one more question? All right, so we can thank the team.